Microprocessors are the brains of modern electronics. They are tiny but powerful chips that control everything from smartphones and laptops to cars and airplanes. Without microprocessors, our world would be very different. We rely on them for communication, entertainment, transportation, and much more. They have revolutionized the way we live, work, and interact with the world. Imagine a world without computers, smartphones, or even digital clocks. This was the reality before the invention of the microprocessor. The microprocessor, a tiny chip containing millions or even billions of transistors, changed everything. It brought about the digital revolution, making technology more powerful, compact, and affordable. From the sleek smartphone in your pocket to the sophisticated systems in spacecraft, microprocessors are at the heart of it all. They are the unsung heroes of the digital age, powering the devices and systems we often take for granted. Understanding how microprocessors work can seem daunting, but the basic principles are surprisingly simple. Let's start by delving into the fundamental language of computers, bits, and logic gates. At the most basic level, computers understand only two states, on or off, represented as 1 or 0. These binary digits, called bits, form the foundation of all computer data and instructions. Bits are grouped into bytes, typically consisting of 8 bits, to represent more complex information like letters, numbers, and symbols. Everything a computer does, from processing complex calculations to displaying stunning graphics, boils down to manipulating these bits. But how are these simple ones and zeros transformed into meaningful actions? This is where logic gates come in. Just like the alphabet forms words and sentences, bits are combined to create instructions and data. These bits are manipulated within the microprocessor using logic gates, which are electronic circuits that perform basic logical operations. These logic gates, using transistors as switches, form the bedrock of computation, allowing microprocessors to perform a wide array of tasks by combining simple logical operations. Logic gates are the fundamental building blocks of digital circuits. They take one or more binary inputs, 0 or 1, and produce a single binary output based on a specific logical operation. Common logic gates include AND, OR, and NOT gates. The AND gate outputs a 1 only if both inputs are 1. The OR gate outputs a 1 if at least one input is 1. The NOT gate simply inverts its input, turning a 1 into a 0 and vice versa. By combining these basic gates in various ways, complex logical operations can be performed. These simple logic gates, when arranged in specific combinations, can perform arithmetic operations like addition and subtraction. This is where the arithmetic logic unit, or ALU, a crucial component of the microprocessor, comes into play. These combinations of logic gates form the building blocks of more complex circuits such as adders, multiplexers, and memory cells, which are essential for performing arithmetic operations, data selection, and information storage within the microprocessor. The ALU is responsible for performing arithmetic and logical operations within the microprocessor. It's like a tiny calculator that can add, subtract, multiply, and divide binary numbers. It also performs logical comparisons, such as determining if one value is greater than, less than, or equal to another. The ALU receives data from registers, which are small, temporary storage locations within the CPU. The ALU then performs the specified operation and stores the result back into a register. The control unit, another vital component of the microprocessor, dictates which operations the ALU should perform. The ALU's operations are governed by the microprocessor's instruction set architecture, or ISA, a collection of instructions that the processor understands and can execute. Section 5. The instruction set. Architecture, a common language. The instruction set. Architecture, or ISA, acts as a bridge between software and hardware. It defines the set of instructions that a programmer can use to tell the microprocessor what to do. Each instruction in the ISA corresponds to a specific operation that the microprocessor can perform. The ISA specifies the format of instructions, the operations they perform, and the data types they operate on. It also defines how the microprocessor interacts with memory and other components of the computer system. Examples of ISAs include x86, ARM, and RISC-V. When a programmer writes code in a high-level language like C++ or Python, that code is eventually translated into machine code, which consists of instructions from the microprocessor's ISA. This machine code is what the microprocessor ultimately executes. Section 6. Control Unit, the conductor of the orchestra. The control unit is responsible for fetching instructions from memory, decoding them, and directing the other components of the microprocessor to execute those instructions. It ensures that the correct data is retrieved from memory. The ALU performs the appropriate operations, and the results are stored in the correct locations. The control unit operates according to a fetch-decode-execute cycle. It fetches the next instruction from memory, decodes the instruction to determine the operation to be performed, and then fetches the necessary data from registers or memory. Finally, it signals the ALU or other relevant units to execute the instruction. The control unit is like the conductor of an orchestra, ensuring that all the different parts of the microprocessor work together in harmony. It orchestrates the flow of data and instructions, ensuring that programs are executed correctly and efficiently. Section 7. Pipelining, the factory line of instructions. To increase efficiency, modern microprocessors employ a technique called pipelining. Imagine an assembly line in a factory where each stage performs a specific task. Similarly, in pipelining, the execution of an instruction is divided into multiple stages, and each stage is handled by a dedicated part of the microprocessor. While one stage is fetching an instruction, another stage can be decoding a previously fetched instruction, and yet another stage can be executing an even earlier instruction. This parallel processing significantly speeds up instruction execution, as multiple instructions are processed concurrently. Pipelining is analogous to an assembly line, where different stages of instruction processing occur simultaneously. This parallel processing greatly enhances the microprocessor's throughput, allowing it to execute instructions at a much faster rate. Section 8. Advancements in CPU architecture. Over the years, microprocessor architecture has advanced significantly, leading to faster and more powerful CPUs. One major advancement is the development of multi-core processors, which combine multiple processor cores on a single chip. Each core can execute instructions independently, enabling parallel processing and significantly improving performance for multitasking and running demanding applications. Additionally, cache memory, a small and fast type of memory located close to the CPU, stores frequently accessed data and instructions. This reduces the need to access the slower main memory, further boosting performance. These advancements, along with innovations in transistor technology and power management, have led to the powerful and efficient CPUs we have today. Section 9. Emerging architectures. As technology evolves, new architectures are emerging to address the demands of specialized applications. AI-optimized processors, for example, are designed specifically for machine learning tasks, featuring hardware acceleration for matrix operations and deep learning algorithms. Quantum computing, a fundamentally different approach to computation, leverages the principles of quantum mechanics to perform operations on data represented by qubits. Qubits, unlike classical bits, can exist in a superposition of states, allowing quantum computers to tackle problems that are intractable for classical computers. While still in its early stages, quantum computing has the potential to revolutionize fields like medicine, materials, science, and artificial intelligence. These emerging architectures highlight the continuous innovation in microprocessor design, driven by the ever-increasing demand for computational power and efficiency.